At some point, we will be required to do hexa to octal conversion, and this is the easier part because we just need to pass through the decimal number system, because we have already seen that with the hexa number, you can represent it using binary numbers, 4 of them for each digit, and then once you have formed your 4 binary digits representing each hexa number, then you can group them into groups of 3, which we can now convert to octal number. Therefore, the hexa number is converted to binary form first, and then the binary sequence is sectioned into groups of 3 bits. So this is the easiest route. Say you have a hexa number, say 1D. 1D can be represented as, this is equivalent to 1 and 14, which you use 4 digits to represent each of these as 0001, representing 1, and 14 is represented by 1110. So this is your binary equivalent. So if you group now these 3 into the groups of 3 bits each, you end up with 110 is equivalent to 6 and 011 is equivalent to 3. And therefore, you can say that 1D in base 16 is equivalent to 36 in base 8. So the easiest route here is passing through the binary number system. So each group is converted directly to octal, and the conversion of octal to hexa is performed in a similar way. So again, we can have an octal number, say 36, like we have seen in octal. You want to convert it to hexa. So what is it going to be? What you do, you convert this into its binary equivalent. You simply say 3 is equivalent to 011. Again, we are forming 3 bits. 6 is represented by 110, and therefore you regroup these into groups of 4, starting with the decimal point going left. So this will be equivalent to 1, and this is equivalent to 14, which we have seen is representing D, and therefore you are able to get your hexadecimal back. So we have an example that involves hexa number to octal conversion, and we do it the same way we have illustrated. We say C is equivalent to 12 and D is equivalent to 13. 7 is still 7 and E is equivalent to 14. So what we do is do it simply, represent each of these hexa digits into their binary equivalent, which is 1100 for 12, 1101 for 13, this is 0111, and 14 is 1110. So you know that we have a decimal point here, so we are going to be grouping them to the right and to the left into groups of 3. So here I have my 3 represented by 5. 100 is 1, and 1111, which you can have a 0 there, is equivalent to 3. And on the other bit, we start grouping them into 3, and what we find is we have 011. This is equivalent to 3, and 111 is equivalent to 7, and 100, we can always add a 0 at the end, is equivalent to a 4. So the final answer in octal of this number is actually 315.374. We want to do another hexa to octal conversion just to be sure that we are able to perform this simply. This is an octal number. Now we want to convert it into hexa. What we do is represent each of these. Remember, this is now in octal. We want to go to hexa. We are going to be converting it to binary, and it represents each of the digits in 3 bits equivalent. 7 is 111, 2 is 010, 5 is 101, 0 is 000, and 1 is 001. So then we group them together. Our decimal point is at this point. We want to group them into 4, so our first 4 will be there and the other 4 will be there or not there, stopping at that point, and then we have the last one going to the left, and the other one is starting here. We have 4 and we have to have 00 there. So what we do is 0101 is equivalent to a 5. 1101, that is a 13, and this is 000, which is a 1, and this is a 0, and this is a 4. So what we do is that we want to convert this to be D. This is 1 and this is 5. Point, our decimal is still at the same point, 04. And therefore we are saying 725.01 is equivalent to 1D5.04, which is in hexa.